Today's lesson, we're going to look at giant ionic structures. So remember, ionic compounds are made from a metal and a non-metal, and they all form a giant ionic lattice or a giant ionic structure. So we need to look at what these words mean. Very important in chemistry is that you learn your structures. So you have your giant ionic lattice. All ionic compounds form this. So giant ionic lattice. So what do these words actually mean? Well, a lattice means a pattern. So it's a regular arrangement of particles. The word giant means that we don't know how many ions are present, but it's a very large amount. So the pattern keeps repeating indefinitely, and it'll depend on the crystal exactly how many ions you have. So these are crystal structures. So if you look at a diagram of this, you might have seen it in your lab with magnets where they hold each other together. So that's one version of it. Then you might see this version of it as well, where they show the ionic bonds. Each has its pros and cons, and that falls under the atomic model. But ultimately, this is what giant ionic lattice looks like. And in all these famous examples, the chloride ion is the green one, and the gray one is the sodium one. So this is sodium chloride, in other words, table salt. So if someone says to you, what structure does table salt form? You would say a giant ionic lattice. Okay, now back to this. The key properties you have to know are the boiling point and the conductivity. So the first kind of famous question is, do ionic compounds have a high or low melting point? The answer is high. The reason is the Seth-Boki. They have strong electrostatic forces between oppositely charged ions. Therefore, a lot of energy is needed to break these forces. So in a giant structure, you have to break the forces of attraction. In this case, we have positive metal ions and negative non-metal ions. They're going to attract. You need to break that apart by using energy. So this can be worth 3 marks. The first part is 2 marks, the Seth-Boki, and then you always have to link melting points to energy. So therefore, a lot of energy is required to overcome these. Now, you might want to consider, let me just rub this guy out. Second. Okay, back to this. If you consider now, this is a bit of an extension. What has a high melting point, NaCl or MgO? Well, you have to think of the charges. Na group 1 is +1, Mg is +2, because it's in group 2. Chloride is Cl minus, oxide is 2 minus, or -2. You can clearly see that the magnesium oxide has double the charge. It has +2 and -2 versus +1 and -1. And it so happens that the bigger the charge, the stronger the ionic bond. That is the rule. If you progress onto A level, you'll actually learn a bit more about charge density and stuff like that and the actual size of the ions. But the main thing for GCSE purposes, if you ask for a direct comparison, is that the bigger the charge, the stronger the ionic bond. And then you have to add that icing on the cake mark, so more energy is needed to break these forces. Okay, next is the conductivity point. And the point is, say to yourself, does table salt conduct electricity? Well, you'll think, no, it doesn't, which is the right answer. However, if you dissolve table salt in water, or you melt salt, it happens to conduct electricity. That can be shown in a lab if you connect a circuit together and have a light bulb. You need to know why. Why is that? And the reason for that is this here. Why do ionic compounds need to be molten or in solution to conduct electricity? Well, when the ionic compounds are solid, the ions cannot move. That's actually all you need to say. Ions cannot move and carry the charge, is what you would usually say. Obviously, ions don't have a suitcase to carry the charge, so that is not necessary. But if it's the question's word more marks, it doesn't harm to say it. But the key thing the examiner is looking for is the word move and the word ion. If you say electron, you'll get this wrong. So only in the case of ionic compounds, you cannot say electron, you must say ions. Now, when something is molten, basically heated and melted, or if something is dissolved in water, i.e. aqueous, the ions start to move around. They're mobile, and they can carry the charge. And you can see in the diagram here, where it's been melted. So those are the main points for your syllabus. There is two further properties we can look at, which is this one here. Why do ionic compounds usually dissolve in water? Well, they usually dissolve in water because water molecules are slightly charged. If you go into A level, you'll learn that they're actually polar. So what happens is that the H part of water is slightly positive. So like this, HOH, water. The H is slightly positive, the O is negative slightly, and the H is positive. So if it comes near, say, a chloride ion, they can attract to each other. So for example, if Na, so table salt, NaCl, there's a Seth-Boki, strong attraction between these opposite charged ions. If we call this attraction X, and we call this attraction Y, if Y is bigger than X, i.e. that the water pulls the chloride towards it more than the sodium pulls it, then the crystal breaks up and the ionic bond is broken. If the ionic bond is too strong, then it cannot be broken and it cannot dissolve. So not all salts are soluble in water. That is beyond what you would need normally though for your GCSE, but here's a diagram of it if you're interested. So here the O, which is slightly negative of water, lines up with the sodium, whereas here the H, which is slightly positive from the water, lines up with the chloride. So it pulls the crystal apart. There's one final property, which again is a bit of an extension. Why are ionic compounds brittle? Well, the reason they're brittle, so brittle means when hit at a particular angle, they shatter. That's because if you apply a force to an ionic compound, you see how they're nicely plus, minus, plus, minus. No, sorry, incorrect. They should be alternating. Let's have a look. Ah, this is correct. Plus, minus, minus, plus, and so on. They're all opposite charge and attracted. If we play the animation and we hit the ionic compound, the lattices hit and the layers shift. Now you end up with charges which are the same, plus and plus, minus and minus. And when you get the same charges, they tend to repel each other. So that is why they're brittle. So that's all the properties done. To show you a summary of what we just did in my common questions and answers booklet, this booklet will be attached and everything you have to know on the whole of bonding is done over 2 pages. Today's lesson, we've learned this part. So not covalent, but all the way up to ionic. And all the key answers are here. And that's where you'll find exactly what you have to say in this case of an exam. It even has the charges here for the ions from the ionic formula lesson. So learn these well, because the more you learn of bonding properties, the more you can get confusing which words to exactly use. So for ionic bonding, the key is that ions either move when they're molten or aqueous, or they don't move when they're solid. And that's what impacts the conductivity. Okay, that's the end of this lesson. Next, we look at covalent bonding, dot cross diagrams, and what it is. Thank you.